But are there any questions from what was due 5.4, 5.5? Was that what we did last week, I believe? Something like that. What did we do?
That's due at the end of the day today, correct?
Yeah, that should be
Okay.
due at the end of the day.
Cool.
And
which ones are due? Sorry.
let me double check. Make sure I'm saying the right thing, because I believe we did 5.5 and 5.6 right last week.
Yeah.
Yeah.
5.5 and 5.6 is what I meant to say.
Are due today?
Yeah.
Okay, cool.
So 5.5, 5.6 are due today. The other thing is I have 6.1 notes up, so we should get through 6.1 today. We might start getting into 6.3, 6.4. I put those two together in a section. I know my addendum looks a little different. It looks like 6.1 and 6.3 are together, but like 6.3 and 6.4 are really the two sections that kind of go side and side. And so 6.1, we're going to do functions and systems of equations in two variables. So we're going to do things with two variables. We've looked at things that are linear with two variables. And so we'll do a lot of stuff with sort of like linear functions with two variables. And then we're going to go to three variables. And so then we got to start talking about three space instead of two space. And so 6.1 is about like solving these systems of equations. 6.3 and 6.4, we're going to get to the three variable equations, and then we're going to solve those, which is a little bit more complicated than the two variable stuff. And so we're going to end up using matrices. And so maybe you feel a bit like Neo or Morpheus or something like that. But we're going to enter the matrix, I guess. So let me switch my camera. Here's coming in George. Any questions about anything that's due, anything we have so far? Did I say quiz 4 was up? I posted up quiz 4. That should be up. I think that's it, unless there's any questions about the stuff we're done. Okay. So I told you this is it. So 6.1, functions and systems of equations in two variables. And so this says functions of two variables. What does it say? Consider the process of addition. So we can think about like adding two numbers. If we have, if we have the process of addition, you have to give me one number and you have to give me the other. And so if we're looking at this, I could write it as f of x comma y equals x plus y. And so all this tells me to do is add two numbers together. And so in order to add two numbers, you have to give me two numbers. And so you might notice previously we just have something that looks like f of x. And we had just f of x previously because we only had one variable. This was we had some kind of function with an x over here, and this was like our y variable. So now we're going to have like three variables. And so you can think of f of x comma y as kind of being like a z variable or a third variable. And so if I'm thinking about this, if I see f of 3 comma 5, what that means is I plug in my 3 to my x and my 5 to my y. And if you want to give me a value of 5 plus 3, I'm hoping everyone can tell me f of 3 comma 5 is going to equal to 8. So I could write this. I could write, I don't know, f of 3 comma 5 equals 8. I have a value for this function at 3 comma 5. Okay, so there's a little bit of vocabulary. F of x comma y is a function of two inputs or a function of two variables. It's a two-variable function is typically what we're going to call it. Independent and dependent. So previously we had an independent x, a dependent y. Like the y would depend upon the time, right? The height of the ball would, let me animate someone. The height of the ball would depend upon like the time that it was, right? Now we have two different variables. So this might be like, I don't know, hide a ball in the speed that was pitched, right? Might give you the position, something like that, maybe. So we might figure more stuff into our equation.
So, hello?
Yeah.
So is it actually a coordinate or does it just look like one?
It looks like one. You could consider it a coordinate. That's not a bad thing to do. You could have an x comma y comma z. We're not getting into sort of like 3 variable equations, but when they do, we will look at that as being a ordered triple, right? An ordered pair when we talked about quadrants in the 2 space. When we get to 3 space, you have to give me 3 coordinates, right? You have to give me left, right, up and down, and in and out.
Okay.
So you could potentially look at it that way. This could be a function defined in like 3 space, or you could be defining one variable in terms of the other 2. That is something that could happen. So I can see where you say it's a coordinate, but I would not look at it like as a coordinate like this sort of thing. Maybe I would look at it more. This is just the input that we're putting in.
Okay, so it could be a coordinate, but it's not necessarily a coordinate.
Yeah, pretty much.
Okay.
You can make some kind of weird thing out of it, but it's not necessarily a coordinate. So this is f of x comma y, and we want to plug in f of 2 comma 3. And so f of 2 comma 3 is my x is taking a quantity of 2, so I'm doing 2 times 2. And my y is taking a quantity of 3, so I'm doing 3 times 3. And so I believe this gives me, what, 4 minus 9 or a minus 5? And so we've done these sorts of things before with one variable. And so you're just looking at what's taking place of what. And so my x is taking a quantity of 2, my y is taking a quantity of 3. I plug in everywhere there's an x, I plug in a 2. Everywhere there's a y, I'm plugging in a 3. Same thing down here.
So I mean, this is fairly obvious, but I mean, I don't know if it is, but I would assume that it is. But the first coordinate is always, the first variable is always the x.
Conventionally, yes, that's just convention to go x, y, z.
Thank you.
But like in this next one, right, we can define it. If it makes more sense to define it with other letters, like this, I believe is volume of a sphere. If I remember what, I hope that's correct. I believe this is volume of a sphere. So if you give me no, this would be volume of a cylinder, sorry. And so if you give me a radius and a height of a cylinder, we can figure out the volume of that thing.
But I mean, I guess like the first one always goes with the first one, meaning 3 and R, and the second being 2 and H. Like they're always.
Yes. This order is the same order as this, right?
Okay.
We're keeping the order here. Yep.
Thank you.
So if we're doing V of 3 comma 2, my R is taking or place of 3, or it's taking a value of 3. My H is taking a value of 2. And so this one, and well, in the previous one too, you might notice it depends what order you plug these things in. So R is 3, so we have to square the 3, and we just multiply by the 2. So this is what, 9 times 2 is 18, divided by 3 is 6. I believe this is giving me 6 with a pi. And if you printed out your notes before, like last night, I don't believe this is on there. I threw this on there. I realized they have this in your homework, and it's a weird vocabulary thing that to be honest, like I'm not super familiar with this vocabulary myself. But they give it to you in your homework, and it's worth going over. So the variable z varies jointly with the square of x and the third power of y. So if z is 2700 when x is 5 and y is 3, then find z when x is 7 and y is 2. And so I just want to go over this vocabulary a little bit and talk about what this means. So z varies jointly with the square of x and the third power of y. So the square of x and the third power of y, they're saying this varies with that, varies jointly. And so if we want to put these together, the way that they do it is through multiplication. And about the only other thing here is there can be a constant of variation. And so we need to figure out what our constant of variation is. And so this is the general form. And so I'm hoping this is the thing that you're getting from this vocabulary-wise. Like if you read this, z varies jointly with the square of x and the third power of y, I hope you deduce this sort of thing. And so this next sentence is giving us values to plug in to figure out what our k is. And so if they say z is what, 2700, I don't know what the heck k is, so let that be a variable. I want to do 5 squared, and I want to do 3 to the third. And this should give me 2700 is equal to k times some number. So this is 25 times 9. Ooh, not times 9. Times 27. This is 5 squared times 3 to the third. This should give me 675. And when I divide 2700 by 675, I should get k has a value of 4. And so now I should have a like specific sort of formula. And so my specific formula, it just looks like my general formula. With the k plugged in. Now I have a specific formula. Now they're going to give me some sort of values to use with this thing. So now they want me to find z when my x is 7 and my y is 2. So now I'm just plugging in values 4 times 7 squared times 2 to the third. Was that 8 times 49 times 4? 4 times 7 squared times what? 8. 1568, I believe. 1568. Get it all in there in one shot. And so this is verbal. Like I'm hoping you can do this from the verbal. After we get that, they're going to give us values to plug in to figure out our constant or coefficient. Find the coefficient, plug it back into the specific. Then they're going to give us values to evaluate with. And so that sort of general shape, I know we've had that sort of general shape of going with the general, finding the coefficient, plugging it into the specific, right? Now we're doing it with more variables. Questions? Okay. A linear equation in 2 variables can be written in the form of ax plus by equals k. So we have 2 variables, and they're equal to a number. A and B are not both equal to 0, so we have to have the variables in there, basically. One or the other. And so if we want to think about linear equations, we want to think about the types of solutions that they might have. And so if this is a line, and this line represents like all the solutions to this equation, Where am I at? There we go. Okay. This line represents all the solutions to this equation, and this line represents all the solutions to this equation. What would represent the solution to both of those equations? So if we have a system, the thing that represents the solution to both I hope you can see, is going to be that point of intersection, the point they have in common. So the point they have in common is going to solve both that blue line and that red line. It's a point on both of the lines. And so I think we've had this before, but one of the options when you have a system of linear equations is that you can have one solution. And that solution looks like a single point, x comma y. They're going to give us some sort of number. I don't know if this looks like what, 3, 4. You're going to give me the numbers 3, 4, right? It's got a very specific solution. What do my notes say? The solution is given by the coordinates of the point of intersection. That's what my notes say. This next one, I'm going to tell you there are 2 lines there. You might tell me that looks like one line. You're absolutely right. That is because it's the same line going over itself. And so they might give you the same line, because I can give you the same line with different equations. I can give you 2 different equations that represent the same line. We've looked at examples of that, but it's possible. And so they can give me 2 different equations that represent the same line. If I want to know what points those lines have in common, it is every point on this line. And so if you think about that, how many points are on a line? There.
Infinite.
Yeah, there's infinitely many points, right? And so there could be infinitely many solutions. And what do they look like? They look like points on a line. We'll talk a little bit how to write that look like points on a line. This is a single point. Maybe I could say that. Single point, it's the point of intersection. And then the last thing, I can have one solution, I can have infinitely many. The last thing is they could be what? Parallel. And so if we know parallel lines, one of the ways that people try to define them, I guess, is that parallel lines never touch. And so if they never touch and we know that solutions look like points of intersection, then you might be able to conclude that this has no solutions or 0 solutions. So we can have 0, we can have 1, or we can have infinitely many.
We could also have like a handful, right? Like or just say 2 if there was a negative and a positive parabola that crossed over each other.
We're talking, okay, so you use the word parabola. This section, we're just talking about linear stuff.
Oh, okay.
Yeah.
Okay, thanks.
So if you have a parabola, absolutely, you can have more than one solution. But we're just talking about 2 linear equations.
Thank you.
And so I might want to say it, but like, you know what a linear equation is. A system, I know I've been using the word system, it just means we have multiples of these equations, right? This is going to be like one of the equations, this is going to be the other equation. To make sure I get my vocabulary out there. I just like, sometimes I just make the assumption everyone knows what I'm talking about, and it's not a good thing to do. So this is some vocabulary. If I'm being honest, I'm not the hardest on this vocabulary. Like I look at it every time for class, and I like almost forget it every time before I teach it again. So a consistent system of linear equations has a solution, basically. So they are independent. So if it has one solution, it's independent. If it has infinitely many, they are dependent. And so this vocabulary makes a little bit of sense Because if we look at these are two independent lines. These are not two independent lines. So this would be independent, this would be dependent. These are both consistent. This one is inconsistent. So these are two independent lines. These are dependent. These are both consistent, and then this one is inconsistent. So inconsistent has no solutions. I much prefer you to give me the actual solution than to give me like this vocabulary. I will use it probably because they asked for it a little bit, and you should know it because you have homework to do over it. But my emphasis as a like professor is not going to be over that. Okay, find the solutions to the following equations graphically. So I have both of these things graphed. Identify the system as consistent, inconsistent, or dependent, independent. Okay, so we see this thing, we see this graph, and you might notice it looks like there's only one line here. If you wanted to, you could solve these things. You could put them, if you put them in slope-intercept form, then you would probably see they're actually the same line. And so this is that scenario of the same line going over itself. And so I want to know, is it consistent or inconsistent? So does it have a solution? I guess is the question.
Yes, it has
Yes.
a solution.
It has a solution. Consistent. If it's consistent, is it dependent or independent?
It's dependent.
Yeah, it's dependent because it's the same line. So it's consistent, dependent. Now we want to talk a little bit about like how to write the solution to this thing. And so we're going to write the solution in Set Builder. And so I've kind of mentioned it, but if we have something in 2 space, our solution is going to have 2 coordinates. And so since it's the same line going over itself, the solutions look like things that are on this line. And so I want to like make a little notation. Like there are infinitely many solutions here, right? But that doesn't mean any and all real solutions that are out there. It doesn't mean just any real number that we can pick, right? And so if I'm going over here, like that number is not going to solve that equation. If I pick any point that's not on the line, it's not going to solve it. So I want to talk about the points, but I want to talk about only the points that are on this line. And so to do that, I say I want my x and y. And I want my x and y. Now I give a rule for my x and y to follow. The rule that they follow is one of those equations. So it doesn't really matter what equation you give me, but you have to give me one of these equations. They are the same line, so it really doesn't matter which one you put. But this tells me it's all the x's and y's that follow this rule. And so it tells me it's all the points that are on this line. So I'm hoping you get this notation here down. This gives me the form and this gives me the rule. And so the form is it's an ordered pair. The rule is that it's on the line. Okay. Questions? Okay. Now we want to solve this thing. Is it consistent? Does it have a solution? I'm hoping so. It's consistent. Is it dependent or independent?
Independent.
Yep, it's 2 separate lines, so it's definitely independent. And if it's independent, I'm hoping you can read those numbers, but I'm looking for an ordered pair. And so if they do this, my solution is something that looks like the ordered pair 2, 1. And so for these, I think they're just trying to kind of getting you used to like what your solution could look like, right? It could look crazy like this. If I'm being honest, I think most of the stuff that we solve will probably be the singular solution, right? Sort of like when we had the no solution in Infinity before, most of the stuff we did the solving and stuff with actually gave us a number. It's a little more favorable. It shows like, I think as like as a person that's trying to like evaluate your quantitative abilities, like these are the things that make you do the work, right? These are just kind of like the special cases. You have to know them. They come up. But they're not necessarily the stuff that makes you do all the work, right? We got this one. And what? Inconsistent. If it's inconsistent, we don't even think about dependent or independent. We don't even use those words. So it's just inconsistent. If it's inconsistent, this has no solution. And we talked about this before, but if we wanted to, we could solve these things for y equals. And you might notice that they have the same slope when we do that. They would be parallel. They would have the same slope. So we talked about parallel slopes. So they're just not written in a friendly way to be able to see that right off the bat, right? But it's there. So now we want to talk about solving these things symbolically. We've done them graphically. We know what the graphical sort of solution looks like. So now we want to do things symbolically. So there are basically two sort of methods that we're going to use. There's substitution, and then the second one that we're going to use is called elimination. So if we substitute, basically we solve for one variable, we plug that variable into the other equation. That gives us a one variable equation to solve for, and then we solve for that variable, and then we plug it back in and solve for the other variable. So I know I've just paraphrased these steps, but here they are if you want to read them in all their glorious minute little details there. I would prefer sort of just jump into it. So in 2014, revenue at McDonald's and Burger King totaled $28.5 billion. McDonald's revenue exceeded Burger King's by $26.3 billion. I think I'm just going to do it. Write a systems of equations where the solution gives the individual revenue of each company. Okay, so we want to write a systems of equations. And so I'm going to just use, I'm going to be a little lazy. I really should just define things. I really should put the whole thing. But M is McDonald's, B is Burger King. I should define my variables first. And I know it seems like a little nitpicking thing, but define your variables. I know I'm being lazy, but don't be lazy. It will help you in the end. It will help you when you finally solve things to go back and know what you're talking about. So McDonald's and Burger King. So M and B, if I put their two revenues together, they should total those things. The other thing, McDonald's exceeds Burger King by 26.3. If I want to compare these two, what's the operation I'm putting between these two?
Subtraction?
Yep, subtraction. And so if I'm doing this,
shouldn't it be million? Or am I going in? I could be wrong, quite obviously, but Burger King's revenue by million?
I think it's billions. I don't know if this is accurate. Who knows?
Well, I'm not, yeah, but what, both are billion?
Yeah, it should be.
Okay.
I think it might actually be accurate. I don't know. I have to look it up.
Yeah, well, no, but how can one make more than both of them combined?
This is 28. This is larger.
Yeah, you're right. Sorry, man. Yeah. Let's just say it's early in the
Okay. So we want to do this, and we're doing substitution first. And so we have these two equations. We want to solve them. And so we want to solve for a single variable. And so we got to take one of these equations. It doesn't really matter which. This one. So I want to solve for one variable. And so I think the easier variable to solve for is probably just to add that b to the other side. And you might have started with this equation instead, right? So if McDonald's revenue exceeds Burger King revenue by 26.3, another way to think about that is we have to add 26.3 billion to Burger King to get to McDonald's, right? So there's a few ways you can actually write your equations that might be correct, depending how you interpret it. But this is coming from this equation. And so we want to take this thing, and everywhere that there's an m, I want to plug in this thing. They are the same thing. So I'm looking at this. Instead of m, now I'm writing 26.3 plus b. And I want to add b, and that's going to get me to the 28.5. And so now you might notice, but everything is a first order linear equation, 26.3 plus 2b. And so when we make this substitution step, what ends up happening is we essentially get rid of one variable when we substitute. And so this is what, 28.5 minus 26.3. The difference of those two things is what, 2.2? And so 2b is 2.2. B is going to be what, 1.1? Okay, and so if this was a problem and you tell me b is 1.1, I would be like, what the heck is b, first off? Furthermore, I want to say what? Burger King's revenue is $1.1 billion. And so you should probably actually write me a sentence in English telling me something about this, right? And if you tell me that, I would also be disappointed because you didn't tell me anything about McDonald's, right? And so you got Burger King. Now we need to take our b variable of 1.1. And if we did substitution, you have a substitution step. This is where I would go to find your other variable. So we know m is equal to what? 26. Oh, this is part of it. So m equals 26.3. I want to add 1.1 to that. And so if we do that, that should give me what? 27.4. And what I'm talking about is McDonald's revenue is 27.4 billion. And guess what? We got a singular solution, so I will hurry up with this vocabulary, but it's consistent dependent. Okay. Questions about that? Comments? Shh. Hush. Hello? I think Timothy might be having some problems. I don't know what he's doing over there.
I was trying to be on multiple devices, but there was a delay lag. I was seeing if your voice would come through better on one than the other. So, but anyway.
Okay. So we want to solve this thing symbolically. We're doing substitution. So the best advice I have to give to you on this is to work like smarter, not harder, right? And so we're looking at this, and we want to solve for a variable. We want to solve for a variable by itself. There's something here that kind of sticks out to me. He's like by himself and just kind of asking for it. This guy, right? He's got a 1 in front of him already. He's just like right there kind of asking for it. And so we got to do like one thing. We got to subtract the 5y to the other side. And guess what? That one's already solved for a substitution step. And so now we're ready for a substitution step. This says x is this thing. Everywhere that there's an x here, I want to plug that thing in. And so this should look like 3 times minus 5y plus 13 minus 2y equals 5. And so I do the substitution step. When I do the substitution step, you might notice I'm down to one variable. So this is what, 39 minus 2y is 5. So what, I got to subtract 39 from both sides. I believe minus 17y is giving me, what was that, minus 34? So I'm solving a one variable linear equation, or yeah, one variable equation, and y equals 2, I believe. Now, if you told me this, you're getting a correct solution, part of it. The other thing I have to do is I have to take this thing and I have to go plug it back in. So this says y equals 2, and if you do the substitution, you have a substitution step. It is really ideal to go solve your other variable. So over here, I'm going to solve for my other variable, x equals minus 5. Now my y I know is 2, and I have to add 13. This is a minus 10 plus 13. This should give me 3. Now I want to talk about the solution. My solution looks like 2 things. It looks like an ordered pair. It looks like the x first, followed by the y. And so for the solution, you should really be giving me both of those things. And you should really put them together. If you give them to me like this, okay, you found it. But it should really, like, to clean it up, you should really be putting it into a coordinate. This is what I want to see. This is good work too. I want to see that too. But this is where I want to see it end, I guess is what I'm saying. Final answer. Okay. If possible, find the solution. Okay. So I want to solve for something. This one really is okay. So I guess I'm giving you something with fractions now. They can give you something with fractions. What did I do? So I don't think there's really anything that's going to be easy to solve for here. I probably wouldn't try to solve for this thing. I'd probably definitely go for this thing since it doesn't have a fraction. So I want to either solve for x or y. If I divide by 4, that's not pretty. It's got fractions. But we can solve for one variable or the other. So if I add the 4y over, I divide by 6. This gives me 4 6. I'm going to do a little bit of simplifying. 4 6 is the same thing as 2/3. 3 6 is the same as 1/2. So that went to that equation. This went to this equation. So that's coming from the first equation. And so this is an x. I want to plug in everywhere that there's an x. I want to plug in this equation. So minus 3 times x looks like minus 3 times, now I'm throwing all this stuff in, 2/3 y, plus a half. And I still need the plus 2y. And this is equal to minus 3/2. Okay. And so now I have a one variable equation. So I should be able to solve this thing. 4y. And so now I want to do some PEMDAS distribution first. And so this is a minus 3 times 2/3 is going to be a minus 2. Minus 3 times a half is a minus 3/2. And I have to add 2y. And this is equal to minus 3/2. So now we're looking at this. We see minus 2y minus 3/2 plus 2y equals a minus 3/2. We're looking at this. You might notice we're getting like a minus 2y and a plus 2y. You might notice these two things, right? And I want you to be careful. Some people try to do weird things. I don't know what they do, but they try to do weird things that aren't math. This is going to be nothing. And 0 and a minus 3/2. That is a minus 3/2 on that side. On this side, it is a minus 3/2. And so we're getting this sort of thing. So what does this mean about the solutions? We've had something like this when we solved for variables before. We get minus 3/2 equals minus 3/2. So if I want to, I could add 3/2 to each side. I could get something like 0 equals 0, 1 equals 1. I'm getting something that is true. What does that mean about my solutions?
Infinite amount of
Yeah, there are infinitely many solutions. And so previously, like if this was a one variable sort of thing, and we got this, what they call tautology is what it's called. It's always true. If we get a true statement, it is infinitely many solutions. And so we have this case, and maybe I should go back and talk about what a solution is. So a solution is something that when we go plug it back in, is going to make this true, and it's also going to make this thing true. So it's that search for mathematical truth, right? So we're looking for that truth in here.
But if you put 1 in, you don't get the right answer.
No, not any and everything. We can't just go plug in things willy-nilly, right? And so that's another point I was going to get at in just a second. So we're looking for things that make both of these true. And so this sort of thing happens where our variable like cancels out and we don't get the variable anymore. And so essentially what this is telling us is it didn't matter what we were doing here, right? Anything we plug in here is going to make this true. So we can plug in anything for y, but our x has to follow a certain pattern beyond that. And so what pattern it has to follow is it has to look like an ordered pair, and it has to follow, pick your favorite one to write, it doesn't matter which one, but it has to follow the pattern that looks like this line. 6 minus 4y equals 3. Yeah, that's it. So it is infinitely many solutions, but it's not anything and everything out there, right? And so what this essentially says is it doesn't matter what you plug in for your y, right? It's going to give you a true statement. And so it doesn't really matter what we plug in for a y. We can plug in any real number for our y, and we can always find a correlating x that goes with it. It just has to stay in this pattern, though, right? So there is a certain stipulation that it has to follow. But this does mean infinitely many. There are infinitely many points on a line, but that doesn't mean any and every point out there is on a line, right? Those are two different sort of things. And I know it's kind of weird because when we had infinitely many, previously it did mean everything, right? Here it doesn't quite mean that. There's a little stipulation there. Okay, so that is substitution. But I feel like we've kind of done stuff very similar to substitution, even if we haven't done like substitution proper, right? We've done compositions of functions. Those are very sort of similar, plugging one thing into the other. We've done evaluating functions. That's where you plug one thing into the other. So there's that sort of concept that keeps coming up of plugging stuff into itself, right? And so we have that with substitution. Now we're doing elimination. And so for elimination, you want to set it up in standard form. That's probably the first thing you want to do.
Hey, I'm sorry. Back to number 7.
Uh-huh.
I mean, I don't know. The answer is the thing inside of the whatever those brackets are called.
Uh-huh. Yeah, the set builder notation.
Set builder. Could you? I mean, it seems like the answer is always going to be a coordinate based on the equation, right?
Yeah.
So
yeah, that's it.
So then, was there any need to do all the math? Couldn't you just write, hey, the x's and the y's are dependent upon this equation? So bang, that answers everything.
If you know these are the same equation, right?
So you have to, okay. Yeah, so you have to figure it out.
Yeah, it's not super obvious that these are the same thing right off the bat.
Okay.
Although I think they are if you multiply by -2. If you multiply this entire thing by a like constant factor -2 to the left and right, you'll actually get this one, I believe. And so it is the same equation. It's got another extra little factor in there throwing things off.
Yeah, they're parallel. I mean, I'm sorry, they're on top of each other.
Yeah, it's one on top of the other. Yep.
All right, thank you.
And so yeah, infinitely many, it's always going to look like this. It's always going to be the coordinate and the line that it follows. Elimination, we're going to put things in standard form. We're going to multiply by the same number left and right to one or both of the equations and try to get things that are opposite so that when we add the two equations, they zero out. So I know that's probably a little bit of a load on your brain there. But I think if we jump into it. So they set them up really pretty at first. Because they have them all set up for us. All we have to do is the elimination step. And so if we're looking at this, all we're doing is we're adding the left side with the left side. We're adding the right side with the right side. So we're going directly down this sort of like equal sign. And we're adding left sides, we're adding right sides. So if we add this left side, you might notice we get 2x minus x. There are no more x's over here. If you want to write 0x, okay. If you don't want to write anything, that's fine. No more x's, but we do have a -3 and a +4. This should be giving me a single y. And now we have 4 minus 2 on this side gives me 2. And so what I'm seeing from this is y equals 2. If you give me y equals 2, you did some good work, but you're only halfway there. Now we have a solution. We have to take this thing, we have to plug it back in. So I don't know which one of these looks easier for you. I don't know. I guess I'll do the second one just for kicks. So -2x plus 8 is equal to 4. That means a -2x is a -4, or x is 2. And so if you did this, you went and plugged this back in. You got here, you got here, you got 99.9% of the problem. You just got to put these two things together and give me the ordered pair. Okay. Same thing. These are set up really pretty. And so we're adding down. You might notice 3x, and we got a minus 3x. That's giving me no more x's. This is giving me no more y's. 1 and 1 is going to be 0. And so I want to say this, but like what the next line, what should this next line say? There should really be something here. Because I don't want, there's something that people do.
0 equals 0?
0 equals 0. So sometimes, I don't know, people will try to tell me x equals 0 or y equals 0, right? Don't do this. This is not what it means. So right over here, if you tell me one of these things, it's absolutely wrong, right? That is not true. 0 equals 0. That's a true statement, which means there's how many solutions? We've talked about it. There are infinitely many solutions, is what this means. Don't try to tell me one of the variables is equal to 0. So I want you to like make this distinction. You got to make this distinction at some point if you want to get a decent grade, probably. But getting one of the variables equals to 0 is not the same thing as getting this true statement, right? Those are different things. And so if it's infinitely many, these things look like an ordered pair. They look like an ordered pair such that they follow the line. So pick one of those ones, write it down, pick your favorite one. You usually have at least 2 choices. And the last one, I think if we add this, we're going to get something like 0 equals 4. And I'm hoping by this point, if you get a true statement, it's infinitely many. If you get a false statement, that means nothing would have worked. That means there's no solution.
So just for fun, like if the answer was 2 equals 2, it's still infinitely many. I mean, it's just whatever. It's the same equals the same.
Yeah, so we're evaluating whether it's true or not, right? If we get the same number, and identity is what they call this. Like 1 equals 1, 0 equals 0, that's called your identity. I am myself.
What was the word with a T, I think you said, maybe?
A tautology.
Yeah. Okay.
A tautology is a statement that is always true, or is true of everything.
Okay.
And arguably, like there's some philosophers that argue that they're meaningless. Like if I say it is what it is, right? That's a really famous tautology that people use. It really doesn't actually contribute anything to what's happening. There's some underlying like implications as to what people mean when they say that maybe it contributes. But like the statement itself doesn't actually contribute to anything. It doesn't help you with anything if I just tell you that.
Like Dave Matthews Band is awesome.
Well, it is what it is.
Good one.
Okay. So equals 4, no solution. That's where we are. Oh man, now they're changing things up, making it a little bit harder. And so I might want to say the next section is going to depend a little bit upon this elimination and you understanding like these elimination steps. Because that's all we're going to do when we do matrices. We're going to do this elimination sort of process. And so if you can get this process down when we're doing this today, you'll be even stronger for the next class. So this is 2x minus 3y equals 0, 3x minus 2y equals 5. So we're looking at this. If I add them down, you can try it, but I'm going to have like 3 plus 5, and this is going to give me minus 5. It's not going to get rid of one variable. So we want to set one of these up, and we want to set them up so that they're opposites. So we want to get rid of either the x or the y. You can pick one or the other. I think I'm going to go with x. And so if I want to do my x, I'm looking here and here. And so I'm thinking least common multiple between 2 and 3. So I'm thinking about things that look like 2, 4, 6, 8. I'm thinking about 3, 6, 9. And you probably noticed their least common multiple is going to be the 6. Okay. And so I want to get things to 6. I want to get this top one. I think I'll just multiply this by what? 3. So multiply left, multiply the right by 3. If I multiply the left, I get 6x minus 9y. I multiply 0 by 3. That's really important to do, but it's there. 0 times 3 is 0. Now the book. What's this guy coming in late for? Okay. Now the book. They do everything through addition. So if you want to subtract 2 lines, I guess you could do that. But they do everything through addition. So we want to account for this sort of like negative not being here. We want to put a negative on this thing. We want to multiply this thing. We want to multiply this thing by a 2 to get to 6. But we want to make sure it's negative. And so if we multiply by minus 2, 3x times a minus 2 is a minus 6x. This becomes plus 4y. This becomes a positive 10. So my goal was to get to 6 and to get to the minus 6 here, to set this up like this for the elimination. So to get from 2x to 6x, I got to multiply by 3. To get from 3x to minus 6x, I got to multiply by a minus 2. Now I have my elimination step all set up. I have 6x minus 6x. These simplify. They're not there anymore. These are a minus 5y. And I have an equals 10. If I solve for y, you might figure out that y is a minus 2. And if you get this far, you're about halfway there. And so we need to go plug this back in. You can plug this back into this one, this one, this one, or this one. You have like 4 options here. I would almost never do these 2. They're almost always larger, harder to do. So let's do, I would think that first one might be one of the easiest. 2x minus 3 times a minus 2 equals 0. So this is 2x plus 6 equals 0. So this is 2x is a minus 6. So x is a minus 3. Now I have my solution. My x is a minus 3. My y is a minus 2. I put it together as an ordered pair. So this is the first one that we've had to multiply by something, right? Okay. Okay. So now we want to look at this one. I'm looking here. And I'm looking at either one to cancel my x or my y. So if I'm looking at my x, I'm looking at 3 and 4. And I'm looking at 5 and 7. So this is a sort of like, you can do either one if you want. But like, let's look at them. Let's see if there's one that might be like a little bit easier to do. Save you a little bit of a brain work there, right? So this is 3x minus 5y equals 11, 4x plus 7y. So we're looking at either the LCM between 3 and 4, or the least common multiple between 5 and 7. And so if I'm thinking here, this is 12 and this is 35, and I'm hoping like you're looking right off the bat and you're like, I definitely want to go with that 12. It is smaller, it's easier to work with. I don't want to multiply things to 35. That looks ugly. Okay, so let's do 12. So I need to simplify my x. I need one of them to be positive 12. I need one of them to be negative 12. And so you might have figured this out already. But I got to multiply this thing by 4. And I got to multiply that thing by 4. 3x times 4 is 12x. Minus 5 times 4 gives me minus 20y. And this is equal to 44. And this bottom gets a treatment of minus 3 so that we can get the minus 12. So minus 3 times 4x gives me the minus 12x I'm looking for. Minus 3 times 7y gives me a minus 21y. And then this is equal to minus 3. I have it set up. It's just like asking for it right there. 12x minus 12x. This is no more x's there. I've done the elimination step. I want to subtract 20. I want to subtract 21. I believe that's subtract 41y. And I do 43 minus 3. 44 minus 3 is 41. And so I have minus 41 is y is equal to 41. So y is going to be a minus 1. And now I have a few options. I could plug it into these big ugly things, but probably not. I could plug it into one of these two things. I don't know, 4x plus 7y equals 1. So if I do that, 4x plus 7 times y equals 1. What is this? 4x minus 7 is equal to 1. 4x is 8. And x is equal to 2. And so the last thing I want to do is put these things together. I have my x, I have my y. I can put them together as a coordinate. Questions about this one? I think most of the new stuff is like right up in here, right? All this stuff is kind of, it seems like it's a little bit of maybe repetition. We can multiply the same number to each side of the equation. That is something we can do. We can add two equations. That's something we can do. We can add the left sides to the left sides, right sides to the right sides. And I'll say it, but we didn't do it. We could swap the order these things are in, right? It doesn't matter if we put this one on top or this one on top. Trying to elude a little bit of what might be coming up. Okay. Now they give us two equations. So we have two variable equations, a system of equations. The monthly supply of umbrellas is represented by that equation, y equals 3x, and the demand is represented by y equals 28 minus x, where x is the price in dollars. Okay. So find the price of the umbrella at the store. Hold on just a second. Okay, so they're trying to give us a sort of word problem. And so if we want to know what the price of the umbrella is, we want to know what the x variable is. We want to know the price of the umbrella. So we're going to have a certain price. And you might notice the demand as the price goes up, the demand for the umbrella is going to go down. This is a negative line. As the price goes up, the supply of the umbrella is also going up, right? Who's this iPhone coming in? And so if we want to find the price, we want to know when the supply is equal to the demand. And to do that, they're trying to give us a setup. This isn't my favorite problem. I'd probably have the wording a little bit better. They're trying to give us a setup to solve when these two things are equal to each other. And so we want to know where these two lines cross to give us the price. If we do that, we get what? 4x is 28. So x is 7. Or if we sell an umbrella for what? $7, we can figure things out from there, right? So find the quantity of the umbrellas sold at this price. So we can either plug in that 7 either to 28 minus 7 or to 3 times 7, but y should give you 21. So we have 21 umbrellas. Hey. Questions about this? I know the setup's a little wonky. It's not my favorite problem, if I'm being honest. They don't exactly, this isn't super clear that you're supposed to find the point of intersection, but that's what they're asking. Okay. So I think I'm gonna like stick my toe into the next section just a little bit. It is a little bit longer, so it would definitely like be advantageous to get a little bit of it out of the way. So for 6.3 and 6.4, there's a lot of stuff, and I'm gonna say this. There's stuff in 6.3 that you really don't want to solve until you get through 6.4. They're gonna try to make you do sort of gimmicks that work. But in 6.4, we're going to kind of learn a tried and true method to get through things, to find solutions. And I would much rather you just like do it with technology, to be honest. So for this, usually I like make this advanced notice when we have this class, like, hey, you're going to need a calculator for this section. I realize not everyone may have a calculator that does matrices or be able to get access to it now. So I've put this like link in here. So if you want to click on that link, that's a really good matrix calculator that will help you get these things. And so what we're going to do is we're going to use matrices, and we're going to use matrices to solve these systems of equations. And so 6.3, it introduces like the 3 variable equation. It makes you try to do some stuff with gimmicks. I don't really like doing the gimmicky sort of stuff. It works, and they're not neat, useful math tricks, but I feel like if I make you do too much of them, and then I show you how to do it on a calculator, like y'all are gonna hate me for the rest of your life probably. And yeah, I got enough people hating me. Don't need it. So we want to see if these ordered triples are solutions to the following systems of equations. And so if it's a solution is something that makes the original equation true. So I hope you get tired of me saying that line. So a solution is something that makes the original equation true. If we have a system, guess how many of those things it has to work for? It's got to work in this one. It's got to make this one true. It's got to make this one true. And guess what? It's also got to make this one true. So it has to be true of everything in the system. So we're looking here. We want to see if these things, and I didn't exactly say it, but it's an ordered triple. Well, I said it in the previous chapter, right? An ordered triple is typically, by convention, we give it x, y, z. So I want to plug these things in. I want to see if they're solutions. So if I go -1 plus 2 minus 2 times 2, does that give me a -3? I believe this one actually works. This is 1 minus 4 is a -3. At some point, I hope you see that this is true. So it works for the first one, but I still have to check the rest. So 2 times a minus 1 minus 2 minus 3 times 2, is that equal to a minus 9? This is minus 2, this is minus 2, minus 6. I think this one ends up giving me minus 10 is equal to minus 9. And so right away, if you want, you could go plug it into here and see if it works. I don't think it does. 1, 8, 9, 2, nope. It doesn't work for this one. And so right away, if it doesn't work for one of them, we can automatically just kick it out. I don't think it's going to work for that last one either, but I don't want to waste a lot of time doing it. You can check. If it doesn't work for one, it doesn't work for the system. All right? It's got to work for all of them. If we plug in 1, 2, 3, 1 plus 2 plus 1 plus 2 minus 2 times 3, does that equal a minus 3? This is 3 minus 6. I believe this one works. The next one is 2 times 1 minus 3 times 2. Is that a minus 9? So we're plugging in 1, 2, 3. 1, 2, 3, sorry. So this is 2 minus 2. I believe that's going to give me 0. This is going to give me minus 9. So I believe this one works. I don't want to spend a lot of time crunching these numbers, but you should give me something. You should probably work it down to where it looks pretty close to that, right? Make sure these are true statements. Is minus 4 times 3. Does that give me 13? I don't want to spend a lot of time crunching it, but that's going to give me a true statement. 12 plus 2 is 14, minus 1 is 13. And so you should check each of these, make sure they're giving you true statements. This gives me a true statement. This one gives me a true statement for all three of them. So 1, 2, 3 is a solution to this. So we're going to 3 variables. We can plug in 3 variables to these things. In order for something to be a solution to a system, it has to be a solution to all 3 of them. So previously, for it to be a solution to a 2 variable, it had to be a solution to 2 of them. Now we're going to 3 variables and 3 equations. So maybe you might also want to note that we have equally as many variables as we have equations. That's an important sort of correlation there. You have to have as many equations as you have variables to be able to solve these things. The next thing we're introducing is a little bit of matrix notation. And I think I will hold off a little bit on this. Any questions? Okay, I'm going to hit the stop on the record then.